Hello, this video will talk about graphing rational functions. And a rational function is a function that's defined to be in the form f of x is equal to p of x divided by q of x, where both p of x and q of x are polynomials. And of course, q of x is defined as not being equal to 0. In this course, we look at a few different types of rational functions, specifically the reciprocal of a linear function, the reciprocal of a quadratic function, which we've seen previously in this course, and a linear function over a linear function. But you can use a lot of the same types of tools and strategies as we use to study these types of rational functions in order to extend your thinking and think about other types of rational functions. For example, a cubic over a quartic function. You can start to think about what those rational functions would look like. So our first example, we're going to graph the function f of x is equal to x plus 2 divided by x minus 4. And just like with other types of functions, there's some key characteristics here that we can find fairly easily from the equation. For example, to find an x-intercept, we know that an x-intercept occurs when the y-coordinate is 0. So to find an x-intercept, we're going to set f of x is equal to 0 and solve for the x value. So here we get 0 is equal to x plus 2 divided by x minus 4. And if we multiply both sides by x minus 4, we get 0 times x minus 4 is 0. And if we multiply by x minus 4 on the right-hand side, those two factors cancel out, and we get x plus 2. And now subtracting 2 from both sides, we get that x is equal to negative 2. So we know that negative 2 comma 0 is the x-intercept for this function f of x. So I'm going to plot that on my graph right now. So negative 2 comma 0. We can find the y-intercept using a similar strategy. So for the y-intercept, we know that the x value must be 0. So we set x equal to 0. In other words, we're finding f of 0. And we get 0 plus 2 divided by 0 minus 4. And so f of 0 gives us 2 divided by negative 4, which is negative a half. And so we know that the point 0 comma negative a half is the y-intercept. So negative a half would be located about here. Okay. So because there's a factor of x minus 4 in the denominator here, we know that that's going to impact where a vertical asymptote may show up on the graph. And so a vertical asymptote would show up on the graph where the function is undefined. And a rational function like this would be undefined when the denominator equals 0. So to find the locations of vertical asymptotes, we set the denominator equal to 0 and solve. So in this case, we get x minus 4 is equal to 0. Adding 4 to both sides, we get x equals positive 4. So we're going to show that on the graph as a dotted line. So x equals 4 is located here. So usually we show that as a dotted line, and ideally you would show the equation for that line as well, which is x equals 4. Finally, we can think about the horizontal asymptote. So from what we've seen from previous courses with some of the rational functions that we've graphed there, or the reciprocal function that we've graphed there, they always have a horizontal asymptote of 0. But that's with a constant in the numerator of this function. That's not with a linear function or a quadratic function or any other type of polynomial in the numerator. So in order to find a horizontal asymptote, we can't just assume that it's located at y equals 0. In fact, we already have an x-intercept here at negative 2. So it's not likely that we have an asymptote at y equals 0 as well. So in order to investigate where the horizontal asymptote may be, what we do is we pick extreme positive and extreme negative values of x, and we look to see what happens with the function values. So for example, as x gets larger and larger, so more and more positive, what happens to our function? Okay, so let's pick a really, really large value of x. So let's substitute in, let's say, 1,000,000. So f of 1,000,000 is equal to 1,000,000 plus 2 divided by 1,000,000 minus 4. And that works out to approximately 1.000006. I think I've written the right number of zeros there. So in other words, the function value when x is 1,000,000, a really, really large number, is just a little bit more than 1. And if we play around with a few other large values of x, we see that the larger the x value gets, so the more and more positive x gets, the closer and closer that this number, the function value, gets to 1. Okay. Now, if we look at what happens as x gets more and more negative, so let's pick a really negative value. So let's say f of negative 1,000,000. It doesn't have to be a million or negative 1,000,000, just as long as it's sufficiently large or sufficiently negative enough to make sure that you can see where your function values are getting closer and closer to. So as x gets more and more negative, so we're going to the far extreme left side of our graph, then we get negative 1,000,000 plus 2 divided by negative 1,000,000 minus 4, and that gives us approximately 0.999994. So again, a value that's very, very close to 1, but this time it's just a little bit below 1. So what that tells us is that as x values get really, really large, our y values are getting closer and closer to 1, but approaching from above. So I'm going to eventually erase this arrow here, but just temporarily, I'm going to put an arrow in kind of like this. So we're getting closer and closer and closer to a value of 1, but from above. On the other side of the graph, as x gets more and more negative, we're approaching values of 1, but from below, because 0.999994 is just below 1. So in other words, if we have our horizontal asymptote at 1, this function is approaching 1 from below. Okay? So let's first draw in that horizontal asymptote. So we can see that we're approaching a y value of 1 on either side of our graph, whether we go to the far left or to the far right. So we'll draw in our asymptote at y equals 1. And then we can use the arrows that we just drew in and the x and y intercepts that we already have to sketch in what we think the rest of our graph looks like. So in this corner here, our graph is going to approach that asymptote of y equals 1 on the far extreme left. It's going to go through the x-intercept and the y-intercept, and it's also going to approach this asymptote, the vertical asymptote of x equals 4. And we can also verify that by substituting values that are very, very close to x's 4 into our function equation. For example, I could pick a value of x is 3.999, substitute that into the function, and I would likely get a value that is very, very negative, indicating that this function is getting closer and closer to infinity as the x value gets closer and closer to 4. Sorry, negative infinity as the x value gets closer and closer to 4. Now, on the other side of the graph, we've just got this idea that our function is going to be approaching this asymptote of y equals 1, but we don't really have any other information about what this piece of the graph looks like. So I'm just going to erase that little curve that we had drawn in there. We do know that that's kind of the general shape of the function in that area, but we need a little bit more information. So what we usually do in that case is we substitute other values of x into the function, sort of like a table of values, in order to get a few other points. So here, for example, this y-intercept, that was a point that was 4 units to the left of the asymptote. So I could try substituting in, let's say, x is an 8 and see what the function value is at f of 8. I could also try substituting in basically any x values that are to the right of this vertical asymptote, because that's where I need more information about this function. So let's maybe substitute in an x value of 6 and 8 and see what happens. So if we substitute in to get f of 6, and we have 6 plus 2 divided by 6 minus 4, which gives us 8 divided by 2, which is 4. And so at an x value of 6, the function value is 4. So that gives us a point on the function. And if we try this with 8, so f of 8 is equal to 8 plus 2 divided by 8 minus 4. That gives us 10 over 4, which is equivalent to 5 over 2, or 2.5. So at an x value of 8, the function value is 2.5. And so that gives us probably enough that we could draw in the other part. Actually, I should probably do this in the same color as the rest of the curve. So that gives us enough information to draw in this portion of the graph that goes through those 2 points that we just determined and approaches the vertical and horizontal asymptote. So this is the graph of f of x that we just drew. So again, just to summarize, the information that we used to get this graph was we determined the x-intercept and y-intercept and the vertical asymptote algebraically. We determined the location of the horizontal asymptote by substituting in extreme values of x. And we substituted in a few other x values into the function in order to determine a few additional points, because we didn't really have any other information about that portion of the graph. So ideally, you want to have at least 2 key points that you identify on each piece of this rational function graph. Okay, here's one more example. We're going to graph g of x is equal to 2x plus 3 divided by x minus 5. So again, just like previous, we start with determining the x-intercept by setting g of x is equal to 0. Multiplying both sides by x minus 5, we get 0 equals 2x plus 3. Subtract 3 from both sides and divide both sides by 2, and we get that x is negative 3 over 2, which means that negative 3 over 2 comma 0 is the x-intercept on this graph. So negative 1.5 comma 0, which is here. Okay, the y-intercept, we can determine that by setting x equal to 0. So we're finding g of 0. So that's 2 times 0 plus 3 divided by 0 minus 5. And so g of 0 would be equal to 3 over negative 5, or negative 3 over 5. And so 0 comma negative 3 over 5 is the y-intercept. So negative 3 over 5 would be about here. Okay, our vertical asymptote. We know that we find that by setting the denominator equal to 0. So here that would be x minus 5 is equal to 0. And so x equals 5 would be the equation of the vertical asymptote. Okay. We can find the horizontal asymptote by substituting in extreme positive and extreme negative values of x. And if we do that, we end up with a horizontal asymptote of y equals 2. So I'm going to leave that to you to test that out by substituting in very large, very positive values of x and then very negative values of x, and see what your function values are approaching. But we do get y equals 2 is the horizontal asymptote here. Okay, so we have a pretty good idea of what's happening in the bottom portion of this graph. We've got these 2 points here, and our function is approaching these 2 asymptotes. So we can draw in a nice smooth curve in that section, but we do need a little bit more information about what's happening in this other portion of the graph. So again, we might pick some x values here to substitute in to get some additional points here. So let's try f of 8, or sorry, g of 8 to get another point. So that gives us 2 times 8 plus 3 divided by 8 minus 5, which is 16 plus 3, so 19 over 3. And that would work out to 6 1/3. So at an x value of 8, the function is at 6 1/3. So about here. And let's try maybe g of 10 as well for one more point in that section of the graph. So we get 2 times 10 plus 3 divided by 10 minus 5. And that gives 20 plus 3, so 23 divided by 5. And that would be equivalent to 4 3/5. So at an x value of 10, we have 4 3/5. And again, we can draw in this portion of the rational function curve. Okay, so that's the function g of x.